Good morning, friends. I feel immense pleasure to be here for this video lecture on engineering thermodynamics. I am in the process of power cycles. As of now, I have discussed the 4 power cycle. In that, one group was the reciprocating engines and another was the rotary engines. In reciprocating engine, we have seen the 3 cycles: Otto cycle, diesel cycle and the dual cycle. And the next group, which is the rotating engine, we have seen the Brayton cycle. The Brayton cycle is used for the gas turbine cycle. These gas turbines are used for ships, for the aircrafts, for the power plants and some other purposes, but as of now it is not used for road vehicles because its size is bigger, its speed is very high. These 2 parameters are making the gas turbine engines not to use for automobiles which are on the road. But in near future it may be there for the road purpose. But today I am going to take something different, and this is called the Bell Coleman cycle. It is not the work producing device. It is a work absorbing device. We know by the second law of thermodynamics that heat cannot be transferred from lower temperature to higher temperature without adding some extra work. Here we use the same principle to extract the heat from the lower temperature and we have to deliver to the high temperature. Our rooms, our aircrafts, ships, vehicles, car, everywhere we have nowadays air conditioner, and this all air conditioners are working under the Bell Coleman cycle. This Bell Coleman cycle here we are using as a air standard cycle. However, in aircraft this Bell Coleman cycle is only used, but the basic principle behind all the refrigerators may be the vapor absorption refrigerator, evaporation refrigerator or the air refrigerator. All are having the basic principles are same. In place of the refrigerant, in Bell Coleman cycle we use only air, pure air as a refrigerant, but in the other cycle we use some refrigerant. So I am going to discuss today the Bell Coleman cycle. In this we have introduction to Bell Coleman cycle, Bell Coleman cycle diagram, construction of this PV and the TS diagram, working of Bell Coleman cycle, processes in the Bell Coleman cycle, aircraft refrigeration system, COP derivation of aircraft refrigeration system. These the topics I am going to cover for the today's lecture. In the previous you have seen we have done the Brayton cycle numerical. 2 numericals we have solved for the Brayton cycle, numerical 1 and the numerical 2 just previous to this lecture. Introduction to Bell Coleman cycle. So what is the Bell Coleman cycle? Bell Coleman is an air refrigeration cycle. It is a reverse Brayton cycle which consists of the 2 isentropic processes and 2 constant isobaric processes, which is used to absorb heat from the low temperature cabin and reject it to the high temperature cabin. Okay, just now I have told. Here it is not possible without expending anything to flow the heat from low temperature to high temperature. It is not a spontaneous process, but we are making it spontaneous by expending some work. We are putting some work on the system or the machine. That machine is able to extract the heat from the room and it is sending outside of the chamber. This cycle is used for the both heating and the cooling purpose and uses air as an refrigerant. So here we can cool the room, also we can heat also the room. If we are using as a heat producing, so it is called the heat pump, and when we are cooling it is called the refrigeration system. So here I have given one basic diagram for the refrigerator cycle. So here we have the same way we should have one compressor. So air, it is a cool chamber. Here it is your actual refrigerator. If you see in your home, where you put your vegetables and all the milk and curd and all the items. So this is that place. So what happened here? From here, compressor is taking the air and it is very cool air. This cool air at low temperature and the low pressure, it is entered in the compressor. The purpose of the compressor is to increase its pressure and also increase its temperature. So pressure and temperature is increased. In this, volume is decreased here. From here, it goes to the air cooler. This high temperature and the high pressure is cooled. This is like a radiator. You might have seen in the vehicle in front of your car, first the radiator is coming because this radiator is used to cool your engine. Otherwise, the diesel engine especially, they need some cooling agent. Then only, so it is like a radiator. This shape is like this. These pipes are moving from here to here and it is cooled. If you see your fridge, behind the fridge you have lot of pipes, tubes are there. These tubes are your air cooler. And in the vehicle we call it as a radiator. So here some heat is taken out, cooled at the same constant pressure, and this is entering in the air expander, and this is like a turbine. A small turbine is used, and here the temperature is further reduced, and here it is very, very cool. Very cool is there, and this high cooled, if it is entering and you want to maintain here 1 degree centigrade, this temperature may be minus 5 degrees centigrade or minus 10 degrees centigrade. So this will go and pass on your whole refrigerator and it will make the cool. By this making cool, the temperature of this thing will be increased. And this is happening at the constant pressure. This is also constant pressure here. This is the entropy is a constant, and here also entropy is constant. So there is no change in entropy. So S is equal to C, delta S is equal to 0 and S is equal to C. Here pressure is constant and here the pressure is constant. So this is the process for any refrigerator and how these refrigerators are working. That I am going to discuss in my next slides. So the construction of this thing, this refrigerator cycle consists of the following parts. One is the cooler, then air expander, cold chamber or the refrigerator, then compressor. So what is the cooler? Cooler, it is a cooling device that is used to remove the heat from the high pressure and temperature compressor air with the help of the cooling medium. So the high pressure and the high temperature air which is coming from the compressor is cooled in the cooler, which I have shown you just now. And the next is the air expander. Air expander, it cools further. It is an expansion device that converts the high pressure air into a low pressure air, and the work produced during the expansion is used to drive the compressor. So it is like a turbine, so it is producing some work, and this work is transferred to your compressor. Next is the cooling chamber. It is the space which to be made cooled. When cold air is passing through the cold chamber, it takes the heat from the cold chamber. And then next is the compressor. The compressor compresses the air that comes from the cold chamber to a high pressure. So the purpose of the compressor is to take the cold air with a low pressure, it may make a high pressure and the high temperature. Then only, and here we give the work. We give the work to rotate the compressor. If you see the machine, our electric which we are using in our refrigerator or AC, it is used to operate the compressor only. Okay. So here compressor takes the air from the cold chamber and compresses to the high pressure. The high pressure and high temperature air from the compressor flow to the cooler. In a cooler, heat removes from the air with the help of a cooling medium, which may be water. After cooler, low temperature and the high pressure air passes through the expander. The expander expands air to low pressure and produces work that is used for the driven of the compressor. The low pressure and the low temperature air from the expander flow through the cold chamber, where air absorbs the heat from the cold chamber, which to be cooled and provides a cooling effect. After absorbing heat from the cold chamber, air again flows to the compressor and your cycle is completed. So, compressor, cooler, turbine, then chamber, and again it is entry here. It is a cooling chamber or your refrigerator where your fruits are here. So this is the process for a refrigerator, and this is a working on the Bell Coleman cycle. So what are the processes that we will see here? This you can see here in the PV diagram. 1 to 2 is a compression process. 2 to 3 is a cooling process. 3 to 4 is expansion process, and 4 to 1 is refrigerating effect. So in 4 to 1, heat is absorbed, it is cooled, isobaric, and these are the isentropic. These two processes are isentropic. Okay, so this we can see here. 1 to 2 is a isentropic compression. Pressure raises from P1 to P2. Temperature also from T1 to T2. Pressure and temperatures are raised. Next is the 2 to 3 is a constant pressure heat rejection. QR, heat is rejected. Then 3 to 4 is a isentropic from P3 to P4. Pressure is falling down. And if you see here, temperature is also falling down in a turbine. This is the turbine and this is the compression. Now 4 to 1 is a constant pressure heat addition. Here heat is extracted from, so it is called heat addition. Your air is aiding the heat. That is why it is name is given like this. Now application of this in aircraft refrigeration. Same way it is for the aircraft. So here this is the engine of the aircraft. This is the engine of the aircraft. Air is entering from here. Due to this first 1 and 2, here it is called ram effect. Ram effect means a slight pressure. If you see here 1 to 2 and here TS diagram 1 to 2. Pressure increased from P1 to P2 and temperature also increased from T1 to T2. This is entering into the compressor. In the compressor 2 to 3. 2 to 3 is a compression process. The air which is entering here, it is again compressed. The pressure and temperature is further increased. From here 3 it is entering to the heat exchanger. This is also called the cooler. The heat which is generated by the compressor is cooled from 3 to 4. From here 4 it is going to the turbine. It is a 4 to 5. Temperature is further reduced. Pressure is reduced up to the cabin pressure. This is the cabin pressure. This is the atmospheric pressure. And this is the further. And so from here you reach to the 4 and 5. Now this 5 from this cooled air is entering to the cabin where all the items and passengers, pilots are there. Here it will take the heat. This is the refrigerator chamber. From here it is used. So here due to this heat is increased. So here if you see the temperature is increased from 5 to 6, it is an open cycle. It is an open cycle. From here, this air goes to the atmosphere. So here, due to this rotation of the turbine, a fan is also used. This fan is sucking the air which is entering from here. This air is sucked by this, and this is a cool air. This cool air is cooling this pipe and entering here, and this air is exhausted from here, goes to the atmosphere. So in this way, the cycle is completed. If you see here, the COP of the aircraft refrigeration. So what is the COP? We will see that it is a coefficient of performance. It is always mostly more than 1. So here, if you see the previous process, 1 to 2. So here T2 by T1 is equal to P2 by P1, gamma minus 1 by gamma, and this H2 minus H1 enthalpy is equal to C square by 2 into 1000, where C is the velocity of the aircraft. So this H2 minus H1 is also is equal to Cp T2 minus Cp T1. So this is equal to this. So T2 is equal to T1 plus C square by 2 plus 1000 Cp. So this we got one relation, T2 in T1 form. Now if you take the process 2-3, here it is a compression, so it is MCP T3 minus T2. Oh, okay, this we have already learned. Now the heat rejected in the cooler, it is QR is equal to MCP T3 minus T4. Process 4-5 is isentropic expansion. So here work of the turbine which is producing, it is extracting heat and cooling the again MCP T4 minus T5. Now if you see the process 4-5-5-6, it is an isobaric heat absorption. Here is the refrigeration effect is taking place. So here is MCP T6 minus T5. So now coefficient of the performance is equal to capacity divided by power. Now, how much refrigerating effect and how much work is done. So here we can see this is the your capacity MCP T6 minus T5, and how much is the compressor work? It is MCP T3 minus T2. So this and this, so divided, and this value will be always greater than 1. So COP is greater than 1. So in the next class we will see again the introduction to Bell Coleman cycle, Bell Coleman's cycle diagram, construction, PV diagram, working. These things we will be, again we will do some numericals on this. So these are the references, that is PK Norm, Engineering Thermodynamics, McGraw-Hill's, Eunice Senegal, Michael Bolt's Thermodynamics and Engineering Approach. Any questions you are welcome to ask to my email ydwedi@gmail.com. Thank you very much. Please do subscribe and like my channel and give suggestions if you feel. Thank you very much. Please join for my next lecture, in which I am going to solve some problem and I will derive the Bell Coleman efficiency, Bell Coleman cycle coefficient of the performance, and we will also solve 1 or 2 numericals in my next lecture. Thank you very much for the join.
Like, share and subscribe. Hit the bell icon for more updates.